Here's a fluid mechanics problem that we have to approach using a three-dimensional analysis, but as you'll see, we'll still be able to solve it using Bernoulli's theorem. And if you'd like to see anything similar on the channel, or if you have any suggestions for any topics or specific problems that you'd like to see, let me know in the comments. So let's try to read the question and understand what we have to find. So we're dealing with a vessel, and inside that vessel there is an ideal fluid, and what we've got is a solid object that's within that vessel, and that object has a cylindrical shape and has a radius of r2. Now the depth of the liquid is given to us as lowercase h, and we know that the liquid is flowing out of that vessel and it's leaving through an orifice which has a radius r1 like this. And what we have to find out is the static pressure of the liquid as a function of the distance away from this axis. In other words, I need to be able to say what is the pressure at this point, which is at this distance lowercase r away from that axis of symmetry, essentially. So to approach this, let's try to understand first how the liquid is flowing out. And to do that, I'm going to sort of draw here a diagram which is essentially a cylinder, and this is, in a way, it's like a control volume. So if we were to look at this section here, you can see that this is actually a cylinder seen from a two-dimensional perspective, and if we tilt that slightly, we're actually going to see this drawing here on the right. So we're going to see a cylinder, and then the liquid is actually flowing into that cylinder from all sides. So we have liquid flowing from this side, and then you've got this sort of velocity profile that is happening. And then, of course, you have velocities coming from the other side, and you've got something like this. So we can actually find out what the mass flow rate equation is. So the mass flow rate, the m dot, is given by our usual formula, which is rho AV. And in this case, we've got rho, which is the water density. Now the A, that's the area of the, or the lateral area of the cylinder, which that's given by 2 pi times r times, I'm going to call this d, where d is the height of the clearance, right? So if I were to draw this here on my diagram, that's the distance d, okay? It's not given to us in the question explicitly, we're just being told it's very small, but we're just going to label it with the letter d, and we're just going to keep it as it is. So we have rho times 2 pi r times d, and then times the velocity v. Okay, now we also know that the same mass flow rate, due to the conservation principle, that's equal to the density. Now, I'm also going to look at this here. So I can actually increase the radius of my cylinder, or I can do something else and I can decrease the radius of my cylinder, and I can say that I'm going to now look at a cylinder which has a radius r1. So if I were to draw this here, it would look the same as the drawing below, except it would be a bit smaller in radius, and it would be something like this, right? And I have the liquid going into this control volume from all sides. The only difference being that now my control volume on my cylindrical shape is smaller. Okay, so the mass flow rate, which is the same, is equal to rho multiplied by this new area here, and this new area is 2 pi times r1, right? Because this blue cylinder has a radius of r1, and then multiplied by d. So 2 pi r1 is actually the circumference, multiplied by d gives you the lateral area, and then multiplied by v1. Okay, and what v1 is essentially the velocity of the fluid, well, here. So that's the velocity with which the fluid is escaping that tank, that water tank. So what I can now do is say that this mass flow rate has to be equal to this mass flow rate because of continuity. So that gives us rho times 2 pi r times d times v. That's equal to rho times 2 pi, and then I have r1, d, and v1. Okay, and most of the stuff actually cancels out, so I have those canceling out, I have the d's canceling out, so that gives me that rv is equal to r1 v1, or v is equal to v1 r1 over lowercase r. So this tells us how the velocity changes as we measure the radius away from that vertical dotted line. Okay, so we have an expression for the velocity of the liquid where any distance r away from that axis of symmetry. But that's not what the question is asking us. The question is asking for the static pressure. And in addition to that, we don't even know what V1 is either. So let's try to first find V1. Now, to find V1, we can apply Bernoulli's theorem between this point and, let's say, this point here. So we can sort of follow a streamline that goes from here all the way to here, and we can then apply Bernoulli, which is the following. So we have atmospheric pressure here. So let's call this point 2 and this point 1. So the pressure, the static pressure at point 2 is the same as the atmospheric pressure because there's the free surface. So that's PA plus, and then there's no dynamic pressure, and then plus rho GH. Okay, so, well, there is a bit of dynamic pressure, but it's negligible because the surface area of the water tank is much bigger than the area at the exit, which has a radius r1. Okay, and then this is equal to the static pressure at point 1. Now, the static pressure at point 1 is also equal to PA. Okay, because at point 1, that's where the liquid is escaping the tank, so it's once again open to the atmosphere. So I've got PA plus half rho v, and then we have this velocity here that we're trying to find out, which is rho v1 squared, like that. Okay, so the PA's cancel out, which gives us that v1 will be equal to square root of 2gh. So this is the velocity of the water at the exit point, at point 1, which means that we can now take that velocity and substitute it in this equation, and we'll be able to find what v is. Okay, so we have that v equals v1, which is square root of 2gh, and then multiplied by r1 divided by lowercase r. So the only thing left to do now is to answer the question that the problem is asking us to, which is finding the static pressure at that point here, the distance r away from the axis of symmetry. And how do we do that? Well, we can apply Bernoulli once again. So this time I'm going to apply Bernoulli, let's say, between point 2 and let's call this point P maybe. So between point 2 and point P, I'm going to apply Bernoulli, and this is what we will have. We have atmospheric pressure PA plus rho GH. Again, we have no dynamic pressure at point 2. And then this is equal to the unknown static pressure at P that we're trying to find, plus, and then we have half rho V squared. And there's no potential energy because we're using this line as my potential energy equals 0, my reference line for potential energy, which means that the pressure, the static pressure P, is equal to PA plus rho GH, and then minus half rho V squared. So V squared is just 2GH multiplied by brackets r1 over r squared. So we can cancel out a couple of things. We can cancel out this and the 2, which finally gives us that the pressure at a distance r, so this becomes a function of the distance r, that is atmospheric pressure plus, and then we can factorize the rho gh, and that is rho gh times 1 minus, and that is r1 over r squared. And yeah, this gives us the function of r. So it tells us that the pressure, the static pressure along that clearance, is a function of the distance lowercase r away from that vertical axis here. And this expression that we found using Bernoulli a couple of times gives us that dependence between pressure and lowercase r. And if you want, you can even plot this. And if you do that, you'll have a more visual understanding on how the static pressure depends on that r distance. And that's the end of the question.